In the last class, we learned about the ultrasonic welding process and some important aspects for the success of the welding. Now, it's time for class 2 of the Fundamentals module. Here, we'll understand the acoustic stack and the importance of frequency and tuning of ultrasonic equipment. Shall we start? Here is a mechanical analogy between the acoustic stack and the components of a car. The transducer or converter is comparable to the car engine, as both are responsible for converting one type of energy into another. While a transducer converts electrical energy into a mechanical, vibrating energy, the engine converts chemical energy from pulse into movement. The booster is also similar to the gearbox of the car. So while the booster is responsible for adjusting the proportion between force and amplitude of vibration, the gearbox is responsible for controlling the ratio between torque and speed of the car. That's why they are both comparable. The sonotrode is also comparable to the wheels. It is responsible for delivering the energy generated by the acoustic stack to the welding process. It delivers the vibration. Similarly, the wheels are responsible for carrying out the work of moving the car. That is, they deliver the energy generated by the engine. Another particularly important analogy is the one between the frequency of the acoustic stack elements and the car's gears. Imagine that we have gears with different pitches, different distance between the gear's teeth. What will happen if we try to transmit energy from one gear to another? For example, the pitch of this gear is slightly different to this one. When we try to transmit energy from the first gear to the second, the teeth of the first gear will not fit efficiently into the other. This decreases transmission performance. So, just as the gear pitch needs to be matched, the frequency of each element of the acoustic stack must also be compatible. In other words, the elements of acoustic stack need to be in tune each other. Furthermore, the frequency of the whole stack must be within the allowed tolerance. If the acoustic stack elements are not tuned to each other and in the right frequency, there will be no efficiency in the transmission of ultrasonic energy. If the acoustic stack is not efficient in power transmission, part of the energy will be dissipated in the stack itself. This will cause the acoustic stack to heat up. In turn, this heating up results in more frequency deviation, making the acoustic stack enter a vicious cycle in which frequency deviation reduces the efficiency, creating heat and stress. More heat leads to more frequency deviation. More deviation generates even more heat until causing catastrophic system failure, stopping the machine and damaging the stack, the generator, or even both. This graph represents the common behavior of ultrasonic devices regarding their electrical impedance independence of frequency. The graph shows the electrical impedance offered by the acoustic stack according to the frequency applied to it. For example, if a generator applies 20 kHz to the acoustic stack, it will offer an impedance of nearly 100 kΩ. If for some reason the generator applies 20.1 kHz, the impedance offered by the stack drops to just over 10 kΩ. This is a 90% difference. Alternatively, if the generator applies about 90.6 kHz, the impedance will almost short-circuit. Small frequency deviations cause huge changes in the impedance offered. At this moment, we have already begun to understand the importance of tuning and the stack's frequency. There are two specific and important regions in this graph. They are the resonance and the end resonance. The parameters at these points are known as resonance frequency, Fr, resonance impedance, Zr, and resonance frequency, Fa, and anti-resonance impedance, Za. The resonance impedance, Zr, is the value of the lowest impedance that the stack offers. The resonance frequency is the frequency at which the stack offers, Zr. On the other hand, the anti-resonance impedance, Za, is the value of the highest impedance that the stack offers. And the anti-resonance frequency is the frequency at which the stack offers, Za, or the maximum impedance. There are mainly two types of ultrasonic systems: those that operate at resonance and those that operate at end resonance. Equipment that operates at resonance normally requires a very large amount of force. The electrical current is maximum and electrical impedance is minimal. On the other hand, those operating at end resonance have a large vibration amplitude and a low current consumption because of the high impedance. Mostly, ultrasonic weld machines operate at end resonance, and the generators have manual adjustment or auto-tracking to compensate slight frequency deviations. However, the tolerance range is narrow, and ensuring the stack tuning in the right frequency is essential to proper generator operation. Note that the acoustic stack shown in the example is tuned to 20 kHz because the maximum impedance takes place at 20 kHz. This means that when 20 kHz is applied to this stack, it offers maximum electrical impedance while consuming lowest current. In this other example, the stack is not tuned to 20 kHz. The maximum impedance does not match 20 kHz. So, what happens when a generator tries to operate at 20 kHz with this stack and it is not able to compensate the frequency deviation? Overload. This stack offers a much lower impedance at 20 kHz. The operating frequency of this stack is almost 20.2 kHz. The stack has a deviation of less than 0.2 kHz from the generator frequency, which is 20 kHz. That's less than 100% deviation. However, the impedance offered by this stack at 20 kHz will be 1 kΩ. This impedance is 100 times less than what is expected, which will cause an overload of current in the generator, causing an error or even damaging it. It is also possible to damage the acoustic stack itself. This is the reason why tuning the stack elements to each other and to the right frequency is so important. In the next class, we will learn how necessary it is to have a properly tuned stack, but also why it's not sufficient for its optimal operation. As well as this, we will understand how the coupling is also responsible for the performance of the weld. See you there!